Good morning, everybody. So here we are continuing to talk about sequences. And you had the last video had a little bit of an introduction to these, and we're going to talk about them more deeply this time. So first of all, the limits of sequences. So we have if an is a sequence, or just if a is a sequence. Remember, a sequence is a function where the domain is the set of natural numbers. So n would be 1. N is the domain here. So n is 1, 2, 3, 4, 5, etc. The domain doesn't include numbers like 2.5 or -8. They're all integers and they're all positive. The range could be anything. The range could be fractions, negatives, irrationals, but the domain is positive integers. So it only makes sense to talk about the limit as n approaches infinity, because remember, n is the domain, and n can never approach negative infinity because the domain is positive numbers. So if the limit is a finite number, and we just call that L, then the sequence itself converges. That's a vocab word we need to know. So converging means two things kind of like come together. So this limit, this sequence, if it approaches a number, then it converges, and we say it converges to that number. So a real number, so we're talking about a number that's on the real number line. A lot of sequences don't converge, so we say that they diverge. So when n gets really, really large, so when I've got like the 100th term, the 200th term, etc., is the limit itself approaching like a non-real number? Like, is it approaching infinity or negative infinity? If that's the case, then it diverges. So let's take a look at some examples here. So I've got 6 sequences. Some of them are listed out, the first several terms, and some of them are not. So let's try to think this through. Now here's the domain, all positive integers. Here's the range for this specific sequence. Now, are these numbers getting close to a number on the number line, like a real number, or are they approaching infinity or something? Well, I keep on adding 7, so it's getting bigger and bigger and bigger. So when I get to the 100th term, I'm going to be adding 107. So as n gets bigger, so do these range values. So this one diverges. If you said diverges, that's great. This limit approaches infinity. The numbers just keep on getting bigger and bigger and bigger. This one, well, 1/5, and then 1/25th, and then 1/125th, 1/625th. Well, the numerator is staying the same. The numerator is just 1. The denominator is getting bigger and bigger and bigger. And we've studied this type of number before. If you have one pizza and you have to serve many, 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 many people, then essentially everyone gets nothing. And the math word for nothing is 0. So as this sequence moves along, this is only the 4th term. So when I get to the 100th term, it's going to be really, really close to 0, right? So this one converges, and it converges to 0. That is the real number that this sequence continues, that converges to. So again, if you were to just extend the sequence out dozens and dozens of terms, this is only the 4th term, but if you even go a couple of dozen out, you will find that those numbers are very, very close to 0. So the sequence itself converges to 0 when n approaches infinity. What about number 3? The sequence is 3, -3, 3, -3, 3, -3. It just keeps on oscillating between 3 and -3. So if I go out 1,000 terms, it's either going to be 3 or -3. So it never really lands on one specific number. It's always bouncing. It's oscillating between 3 and -3. So that diverges. It doesn't land on one number. What about our 4th example? So looking at the numbers here, I think it's difficult to kind of ascertain what the sequence approaches. It's easier if you look at this right here. So remember, we want to find, does this sequence approach a real number when n gets really big? And if it does, then it converges. And if it doesn't, it diverges. Well, when n gets really big, -4 divided by a really big number, doesn't that become 0? -4 divided by a really, really big number approaches 0. So when n gets large, this sequence approaches 0 plus 1. So this converges to 1. These numbers get closer and closer and closer to 1. Again, because when n gets large, like even if n is 100, or maybe 100 isn't big enough. Maybe if n is 1,000, do -4 divided by 1,000. That's a really small number. It's -0.004. And if I add 1, it's really close to the number 1. If I add 1 to that, it's 0.996. If n is 1,000,000, well, -4 divided by 1,000,000 is -0.000004. And if you add 1 to that, you get 0.99996. So the bigger n gets, the closer this gets to 0. And 0 plus 1 happens to be 1. If this were plus 8, then it would have converged to 8. These last two bring us back to Unit 2, when we talked about rational functions. And these are both rational functions, and when n gets large, notice the degree is the same on top and bottom. So the 5 and the -8 really don't matter, but it's a battle between 2n and 7n, and they're both of the same degree, so they're both increasing at this almost the same rate, but the ratio is 2 to 7. So this one does converge to 2/7. If we were to extend the sequence out many, many, many terms, eventually it's going to be very, very close to 2/7. It'll never get there, but it's approaching 2/7. And then finally this one, well, the denominator has a bigger degree than the numerator. So the denominator is growing much, much faster than the numerator. In fact, it's growing n times faster. So this is a case where you're dividing by a large number, a relatively small number by a relatively large number. So that means it converges to 0 again. There are two main types of sequences that we're going to study, arithmetic and geometric. So if it's arithmetic, then to get from one term to the next, you just add something. You add or subtract something. And that something is called the common difference. If it's geometric, to get from one term to the next, you multiply something. And that something is called a common ratio. So arithmetic, you just add or subtract the same thing over and over and over again. So arithmetic, that's like the line. And the thing that you're adding and subtracting is the slope. Geometric, that's like an exponential function. And you keep on multiplying the same number to get to the next term. Our first example was the Fibonacci sequence that we studied. Fibonacci, remember, was 1, 1, 2, 3, 5, 8, etc. This is not arithmetic and it's not geometric because you can't add the same thing to get from one term to the next. Here you have to add 0 to get the next term. Here you have to add 1 to get the next term. And then you have to add 1 again, and then suddenly you have to add 2 to get to this term. So you're clearly not adding the same thing over and over again. So it's not arithmetic. And it's not geometric because you don't multiply the same thing to get from 1 to 1, 1 to 2. To get from 1 to 1, you'd have to multiply by 1. But to get from 1 to 2, you'd have to multiply by 2. To get from 2 to 3, you'd have to multiply by 3 halves. So you're not multiplying the same thing. You're not adding the same thing. So it's neither one of these. Let's look at these sequences. 1, 2, 3, 4, 5, 6. Are we adding the same thing, or are we multiplying the same thing, or neither one? We are adding. We keep on adding 1 to get the next term. So arithmetic. This was the Fibonacci sequence that we just talked about, so that's neither. Let me make another group for this is neither arithmetic nor geometric. What about this? 3, -6, 12, -24, 48. I keep on having to multiply by -2. 3 times -2 is -6. -6 times -2 is 12. 12 times -2 is -24. So I keep on multiplying by -2. So this is geometric. What about this one? Definitely not arithmetic, because you'd have to add -7,200 to get the next term. But if you add -7,200, you don't get this. Here, this is geometric. You keep on dividing by 10, which is the same thing as multiplying by 1/10. This one, geometric again. You keep on dividing by 2, which is the same thing as multiplying by a half. This one, natural log of 7, natural log of 14, natural log of 28. I love this example when we get to this stage. This is arithmetic. Why? If you thought that, that's absolutely great. Because remember, natural log of 7 plus natural log of 2 is natural log of 14. If you're adding 2 logs, you multiply the powers. And natural log of 14 plus natural log of 2 is natural log of 28. So this one, that was arithmetic. You keep the common difference, you keep on adding natural log of 2 every time. And then our last one, 1, 2, 4, 7, 11, 16. I'm not adding the same thing, I don't think. Am I multiplying the same thing? Well, to get from 1 to 2, I'd have to multiply by 2. To get from 2 to 4, I'd have to multiply by 2. So it looks like it's geometric, but if I'm multiplying by 2, 4 times 2 is 8, and I don't have 8, I have 7. So it's not geometric, it's neither. The pattern here is you add 1, then you add 2, then you add 3, then you add 4, then you add 5. So this pattern is not arithmetic, nor is it geometric.